All right. So the last day before I return. So what I decided to do is kind of do another chapter 3 topic, something that's quick and easy, so you can just grab it and run with it. So that's that. I think, in fact, the time-consuming part of notes, which it's not going to be, is just copying the problem down. Normally I would have this stuff printed out for you, but I am going to have to write this out due to the nature of things. But once I go over these two theorems, which are basic, they're polynomial identities. They both use synthetic division, so that's always been kind of a simple thing to do. I'll show you that algorithm. If you, I think 7th hour did it. Can't remember if 3rd hour did it. But anyways, we'll talk on Monday. I will be returning Monday. I'm feeling so much better. Very excited about getting back to normality, and my mobility is good, but my left foot is definitely not weight bearing, so I can't actually I can't fall again. So I just cannot use the scooter. I can, and my leg is strong enough to use it now, and it's good, but it's like I don't know why I'm explaining to you. I'll explain it on Monday, but I definitely have to be more stable and stay in a wheelchair. Okay, it's not like I won't walk on my foot again. It's just that it's like I have to make sure that I don't hurt it any further. Okay, so until it heals, I will be in a wheelchair. So a remainder theorem is a unique thing that is kind of crazy how it works, but it allows you to really do something kind of amazing, and I'm going to show you what it will do. Okay, and what it will do is it will take a very long polynomial function. Let's say that you've got this crazy 5th degree polynomial, and I'm going to make sure to copy this down very carefully. Okay, this crazy 5th degree polynomial with all these terms. Okay, and minus 39. Okay, now that's crazy, right? Now, it's not that crazy. It's a large polynomial. And if we graph this, it would look a certain way. This would be a positive odd function. So we know that the end behavior is a certain way. But what if I wanted to ask, what happens when x equals 5? Okay, what would you do? Okay, in fact, what we're asking really is, what is f of 5? Okay, so what we're saying is the function f, this big polynomial, okay, with its variable being x, if we plug in a 5, that means that we would plug in a 5 for each one of these x's, okay? Now that's going to be time-consuming even for your calculator. And I betcha you make a mistake in your calculator before you make a mistake when doing synthetic division. Sometimes, okay? So what happens then is, this is really cool. In order to use synthetic division for this, okay, what you do is you take the number, you do not change his sign, and you put him up there in the window, okay? And you're going to set this up just like we did earlier, okay? And I'll just kind of explain the algorithm again. But what you do is you take all of those coefficients and you put them right in front. You get rid of all of the x's. You do not have to type in this into your calculator. If you are careful, this is going to work out very nicely. Okay? All right. Now, the remainder theorem says that if I perform synthetic division here, okay? All right, so synthetic division is I drop the 3, okay? And then I multiply this guy to this guy, and then it bounces back up against the line, okay, over the line. So now this becomes 15. Now we add those two together, okay? And you get a positive 1. 5 times 1 is 5. Add going down, negative 3. 5 times negative 3 is negative 15. Add those going down, and that is negative 6. Multiply those two, negative 30. Add those two, you get a positive 6. 5 times 6 is 30. Add those together is -9. If I plug in a 5 into this function, into my calculator, and hit enter, okay, I'm going to get -9. Okay, it's amazing. It's really incredible how synthetic division basically takes the 5 and runs it through all of the powers here, and then ultimately gives you the answer. Okay, that's what the remainder theorem does. It's super cool. Okay, so let's ask a second question then. So the answer is actually f of 5 equals -9. Okay, that's it. Which means that 5, -9 is it's one of the points of the polynomial. All right, let's do another one. What if you have g of x? Are these all long? No, they're not all long. Thank goodness. Okay. No, gosh, third one. It's kind of spicy. Okay. All right, so now what we're going to ask is, what is it when x equals 6? So what we're asking is, what is g of 6? Okay. All right, so what is g of 6? So we put 6 in the window, okay, and then we grab all the, now they're all in order, okay, and they go 3, 2, 1, 0, so I don't have to put any zeros there, so that's great. So I've got a 1, because there's an invisible 1 there, got -5, -9, and then 13. Now notice that I'm going a little quicker here because that's what this is designed to do. It's designed to go fast, okay? Now imagine, definitely before the scientific calculator, this is what engineers and mathematicians were doing. They had to do this to go fast. So it looks like, you see how fast I did that. I was talking while I was doing it, right? 1 comes down, 6 multiplies to get 6. Add 1 times, add, multiply, add, final answer. Okay? -5. So that is the remainder theorem. Beautiful. Nice little quick and easy little theorem that is pretty useful and expeditious. Okay, so now let's go to the second theorem. And the second theorem is the factor theorem. And with the factor theorem, okay, with the THM is the theorem. I'm a little sloppy here. But what a factor theorem does is it asks, is a polynomial, okay, divisible by a particular binomial. Okay? And it just basically is a yes or no answer. So that's kind of what's cool about it is it divisible? It means does it go in evenly? Okay. So let's say that our first function here, I'll just kind of show you how it works. And we're not going to prove it in any way. Okay, you've got this polynomial. Okay. Okay, and then we want to ask though, okay, is he divisible? Is x minus 1, and I don't have to put parentheses there, is x minus 1 a factor? Okay, and what it's basically saying is, does x minus 1 go in evenly so that there's no remainder? Okay, so this is very important because if it does go in evenly, then we know that it's a root. But you don't have to know that now. Just know whether or not it goes in evenly. Okay? So if I said, x plus 1, x plus 2 equals x squared plus 3x plus 2, okay, what we would say is these two guys go into this evenly. Okay? There's no remainder that is required to create that. Okay, if I were to make this an 8, okay, that means that these guys probably don't go into there evenly, okay, or one of them doesn't go in evenly. Okay, so what we do is, this one is different than the remainder is only in the sense that we're going to use synthetic division, but what's different is we're going to change the sign of what we see here in the question. Now we're going to ask two questions here. Is x minus 1 a factor, or is x plus 2 a factor? I don't know why I put in there. Just do that. Is x plus 2. So we're going to ask a question. Is x minus 1 a factor? We're going to do it. And then we're going to do the same thing with this guy. Is x plus 2 a factor? Does it go in evenly? So what you do is you take the opposite sign here. That is a -1 there. We will make that a +1. We're going to pull all these coefficients, and we're going to run it right through the synthetic division engine. Okay, so 2, -3, -5, and 6. So let's run it, and then I'll tell you how to interpret the answer. So the 2 drops. All right, so then 2, and then -1, -1, add -6. 1 times -6 is -6. So now I add those together, and I get 0. If it's 0, that means there's no remainder. So therefore, when it's not a remainder, we would say yes, it is a factor. Okay? Now, that's all that you have to say. It goes in evenly, drop it. Okay? What about x plus 2? Okay, now here we have 2, so we're going to have to switch the sign, and you have to do that with the factor theorem. Okay? We still have the same function, so let's just go ahead and do that. So drop the 2, -4, -7, -14. Oh, this is getting large, right? Wait, did I do that right? Make sure. -7. A +14. Then that is 9, -18. Now that is not going to give me 0, okay? So this is -12, and because it's not 0, this means that this guy is, no, he is not a factor. You need a remainder of 0, okay? All right, let's just do one more. Okay, you got g of x equaling x to the 3rd minus x squared plus 17x minus 10. We want to ask ourselves, okay, is x plus 5 a factor? Is x minus 5 a factor? Okay. And they could both be factors. That is a possibility. They could be 2 yeses, 2 nos. We don't know. Okay. Maybe one is, maybe one is not. Let's check. Okay. So let's take the first one, +5. We'll make a -5 here. So 1, -8, 17, and -10. We run it through the synthetic division engine. So 1, or algorithm, -5, -13. That's going to be a +65. Okay, now stop. Clearly, this is going to get out of control, right? The numbers are getting too large, and there's no way that I'm going to get a +10 there to get 0, okay? That's going to be out of the question, so just stop it, okay? That's what's nice about this factor theorem is if the numbers start spiraling out of control, you just stop, okay? But let's check 5. 1, -8, 17, -10. So run it through the algorithm, and we got 1, 5, -3, 15. Okay, so this is a little, okay, there we go. +2, there it is, 10. And that is 0. So we can say that x minus 5 is a factor of this polynomial. Now, we don't know the other thing that it multiplies to get that, but we do know that this goes in evenly, and that's taking us halfway through the battle, and that's all that you need to know for this particular theorem. All right, I'll see you guys on Monday, and then we'll talk about the final and what will be on it and all that good stuff. And also know that all of the grading will be caught up this weekend. I am, again, I might have said this at the beginning of the video. I can't remember. They're all kind of blending together, but you know, I can actually think clearly. My pain is completely under control. Okay, in fact, I'm 0 pain now. So anyways, have a good weekend, and I will see you on Monday.